Okay, good afternoon, everybody. Welcome to this talk. My name is H.R.Tizhoosh. I'm from Systems Design. Today's talk is about big data, medical imaging, and machine intelligence. It's quite three big topics, actually, that nobody can cover possibly in less than an hour. As I said, so since each one of these three fields, plus one that I'm not mentioning in the title, are actually a topic for a 3-hour seminar each, I'm not expecting that we can really go deep in any of this. My own research field is medical imaging and machine intelligence. My first forceful encounter with big data started maybe back in 2005. And by 2008, 2009, I was in a situation that I had to train a neural network with more than 200,000 images. And we immediately realized that's hopeless. You cannot do this. So it's not about MATLAB. It's not about how fast your computer is. So you are in the big data domain, at least when it's still with 200,000 images, you cannot really talk about big data. But if it is two-dimensional data, then you are already on the limits of ordinary computing devices. So as I said, so we want to talk a little bit about really scratch the surface on big data, medical imaging, machine intelligence, and to me, everything wraps up here in the Hadoop. And I like the Hadoop topic here specifically because it comes from industry, not from academia. And as somebody who has spent the past 8-9 years in industry, I know the value of when you develop things in practice. So it's not based on some paper with sound formalisms and theory behind it, but every piece of code is based on countless experimentation and failure and a lot of motivation and energy. So you get things going. And then it doesn't happen every day that something is forced upon us in academia from industry. Then we have to more or less accept something as de facto standard, even if some colleagues may not agree with me in that regard. So first question is, what is difficult, what is big? Because when I say we deal in research, in computer science, in engineering, in mathematics, we deal with difficult and big problems. So what is difficult, what is big? So for example, encryption, decryption is a difficult problem, but it is not a big problem. So if you have introduced the concept of big data, hacking an encryption system is not a big data problem. It's a mathematical problem. It's a very difficult problem, but it's not big data problem. Whereas, for example, forecasting the weather, how the weather would be tomorrow, that's a big data problem. It has been a big data problem. It's a very nasty big data problem. And it's actually one of the first applications where people have started to go beyond conventional computing devices. So not every difficult problem is big. Some of them are. But every big problem is difficult. So to understand that, to get a grasp for that, may not be that easy if we don't realize what is big and what is difficult. So of course, like any other information processing problem, this is about structure, this is about data, it is about data structure, and it is about structure in the data. So when we talk about traditional databases, then we are talking about row column storage procedures. So things come in, we put them in the database, everybody is happy, and you may have a big database, you may need data warehousing. All these things have been around for quite some time, so it's not a big deal. But if you have unstructured data, as we do for emails, websites, videos, images, and many other type of information, if the data is unstructured, and it comes in massive amount, then it becomes a problem. So as a matter of fact, most data on the web in the digital universe, so to speak, is unstructured. So that's one of the reasons that you cannot handle it with all the information and knowledge that we have in traditional data warehousing and traditional databases that we have. And we will keep them, and we will use them, and we will need them for many, many other applications. Big data has its own domain. So what is big? So a collection of data, text, numbers, symbols, sound files, videos, images, so large that conventional databases, computing devices, and software cannot capture, process, and store it. So it has to be really big, and we need some sense of maybe put a threshold and say when we mean big, it has to be at least this, which may not be easy. So, but big data is difficult to store, search, share, analyze, and visualize. As a matter of fact, most big data right now in the digital universe is going unused, specifically in the medical field, where I'm concerned with. We are basically not using the data. So, and the data is going, and we make mistakes because we are not using the knowledge and information in the data. So where does it come from? Of course, we all know it comes from social media, comes from mobile devices, comes from scientific instrumentations, and come from many other things, from sensors, from networks, and other non-scientific instruments. So all those devices generate data as we go. And somebody has to capture it and process it, well, if you want to use it. So there is information in there. So somebody may say, I don't need it. So that in most cases, that would be a mistake to say that. So there have been attempts to define big data more clearly. There are the so-called 3 V's. So the first one is volume. Of course, it has to, the data has to show some exponential increase in its volume to qualify to be called big data. The second V is velocity. So the data comes so fast that you cannot really capture it with ordinary devices. And the third V is the variety. So there are different formats. The huge amount of data generated comes so fast in different formats, and mostly with no or little structure. The lack of structure is a big issue, and there comes also the connection with machine learning and machine intelligence. Well, because, again, conventional techniques that we have, and we need them, and we have to keep them for other aspects of data processing, cannot handle the big data easily. There are other V's. One of them that really matches medical data is very important, crucial in medical data, is the so-called veracity. That data may be incomplete, noisy, not meaningful, uncertain, ambiguous, inconsistent. Then again, this is one of the aspects that you cannot really handle easily with conventional data if part of the data is missing, if data is uncertain. And then you need some sort of machine learning techniques, you need some probabilistic understanding, you need to extract some rules from the data to be able to, in spite of its incompleteness, come to some sort of conclusion. So again, these are the 3 major V's, the volume, the variety, and velocity that everybody talks about. For example, 2.9 million emails sent every second, YouTube 20 hours of video uploaded every minute, and 50 million tweets per day, and so on and so on. So I'm sure the majority of you are familiar with the huge amount of data, the magnitude of the data that is being generated by social media and by the web at large. So when we talk about what is big, there are several topics, several technologies, several fields and domains of technology that are involved. So discovering data is a domain for itself. Hadoop, where I put a lot of my own emphasis with HDFS and MapReduce, is one. Stream computing, data warehousing, conventional and intelligent analytics, integration, quality, security becomes huge. When down the road we put a lot of emphasis on big data, what happens if it is interrupted? What happens if it is not secure? And how you have to redefine quality, we have to redefine many things for big data. Even though the nature of it, when you go down, 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 so when you go to really the basic elements of it, yes, all is still numbers and characters, of course, but its in entirety is a different era of information processing. So what is big? So nobody can really put a finger on it, but up to terabyte. So you cannot really say you are doing big data. And the moment that you get into sub-petabyte or into petabyte area and upwards, then you are talking big data. Of course, this is not a hard threshold. So, for example, a regular network, hospital network, you are talking 500 terabyte of medical image data per year. That's massive because this 2-dimensional data comes with a lot of annotations and other information. That's already big data because, again, I had difficulty with 200,000 images training a neural network. Now you're talking 500 terabyte of image data. That's already big data with respect that the computing devices may not be able to handle it. So World Wide Web is just 1 petabyte. Is small. Is really small. Google Online RAM is 8 petabyte. Annual email traffic without any spam is 300 petabyte. That's huge, gigantic. Daily Facebook data, 30 plus petabyte. Walmart handles 1 million transactions per day. That's 2.5 plus petabyte database. And decoding human genome, 7,000 petabyte took 10 years. Right now, we could do it in a week, in less than a week, if we use distributed computing as it is available today. So 10 years ago, it wasn't available. Not to everybody, at least. So Internet of Things is something that everybody is talking about and is actually being done and is being executed. So you have, for example, the company NAS that just was recently acquired by Google, that you can control the temperature and many things via internet. So if your key is lost, you can do something about it. You can monitor aging family members, and you can share temperature and humidity measurement with everybody. So if all this information, so everything, I was talking to a colleague, he was saying down the road, 5 years, 10 years down the road, everything will be tagged. Everything will be sensor tagged. And this is something to it. No, I'm not sure it will be everything, so I don't want to be tagged as a human being, but I'm sure I will carry on something with me that is tagged. So when we talk about Internet of Things, then all this information, the device is something, the sensoric part is something, the hardware is something, but the data has to go somewhere. And then, again, you can just store the data and not do anything with it, or you have to analyze it somehow and get some information out of it. So we are not prepared for that. We are light years away from being able to, if all this type of devices, Internet of Things, are in place and we are using them, we have, at the present time, we have no capability to process that kind of data. This will go in zettabyte area, so that if everything is implemented, or the majority of ideas. So going to medical imaging, so medical images, so we have different devices. We have CT, we have MRI, we have ultrasound. We use images for diagnosis, for treatment planning, for monitoring, for research. And we save those images in archives using formats such as DICOM. So DICOM is de facto standard of saving medical images, digital imaging, and communication in medicine. If you have not done anything with medical imaging and you hear DICOM format, the standard, that's good news, because that means maybe we have some structure in the data. So when you go deeper, you see, no, that's not the case. So it helps to save and retrieve information in really traditional RDBMS type of devices, but not really structured in terms of big data. So DICOM is not just a format, it's a standard for comprehensive data transfer protocol, guidelines for storage, rules for display, and many other stuff. So the standard should facilitate interoperability of systems. And everybody who uses DICOM, if you go to website of any large OEMs, Philips, GE, Siemens, everybody else, so they have, for every device that they put out there, they have to post online a statement of conformity with DICOM standard. So they have to show that they are conforming to this standard. But having standard is something, enforcing it in reality is something else. So there are many, many fields in the DICOM standard that you have a tag, you have a value, you can provide a lot of information. That has huge potential for big data, not being used at the present time. Most of it is not being used. In radiology, most of it is not being used. For many reasons. Doctors don't have time to do it. They have not received proper training to use it. Many, many different reasons. So if you look at different fields, for example, for creation time, modality, pregnancy status, many, many things. So the header of a DICOM image can have as easily as 100 different fields containing all type of information about resolution, pixel size, who captured the image, what type of device was it, and so on and so on. So there's a lot of information. When you capture the image, that goes in a database, PACS, the so-called PACS, Picture Archiving and Communication System. So you are new into the medical imaging, you hear there's a DICOM standard for saving the image. DICOM is like TIFF, JPEG, PNG. That's great, fantastic. So we have some standard. Then we have some sort of database, which is called PACS. And that raises your hopes. And you say, OK, so we have also archives. But not so. So any image that is captured with ultrasound, CT, MRI, and anything else goes through a network to PACS. And then radiologists through their workstation, they can call it, they can work with it, they can annotate it. They cannot manipulate the data. Nobody can manipulate the medical image. The image is captured, is saved raw. You can add an annotation, but you cannot change the image per se. So the PACS image server has a connection, of course, with the health information system and the radiology information system and the nuclear medicine information system, and is also in connection with the workstation user interface. So everything sounds great. So vendors that provide PACS systems are Agfa, GE, McKesson, Fujifilm, Philips, many, I could list 20, 30. So the problem starts right here. So actually, PACS do not talk to each other. There is no one PACS. They are different. They may not understand each other. And there are a lot of other issues related to PACS. For example, it is difficult to replace them because they come from the companies. It's sort of their IP. So it's difficult to add new application. It is difficult to share data. That's a huge problem for big data. So if I'm going to use the big medical data, I will give you some sense how big that is. If I'm going to use it for some super smart, super intelligent purpose, I need to be able to access it. You cannot. At the present time, we cannot. So it's difficult to integrate with health information systems and can only handle structured data, another problem. So I need something that is flexible enough that can take anything and cannot, because of all that, cannot handle big data. So PACS, where basically every hospital, every clinic on the planet is using some sort of PACS, either from Agfa or from GE or from Philips. They have it, they use it, they store their medical images, but it is not something that we can use to exploit the information in that big data. So we have silos, separate, they don't talk to each other, they don't share information, and they don't let anybody from outside to come in and do anything. So right now what we can do, if you're interested in medical imaging, you can work with some benchmark data. So I can go to Cancer Imaging Archive, I can download more than 200,000 lung cancer images, I can start experimenting with that. Don't tell me 200,000 is not big enough, trust me, it is big enough. So if it can put a rack of 5 computers together and start installing Hadoop on it and start doing something with it. So because if instead of 200,000 you have 1 billion images, it doesn't matter for the way that we do distributed computing because the system will scale up by itself. So that's what is the benefit of distributed computing, like ecosystems like Hadoop. So IRMA project from Germany, ImageCliff is a huge initiative, not just for medical imaging. In medical imaging, actually a small part of it, for image retrieval in general, content-based image retrieval. So sign of hope is VNA. That's coming. Everybody is pushing the clinical side, the medical side. Some small innovative companies are pushing. VNA is coming. So if that comes, if the archives that you have are blind, I don't care it's GE, I don't care it's Agfa, I have a unified system, a universal system that everybody can access, and you have to deal with hospital alone. This is not a vendor issue anymore. That opens the door for big data, for really truly big data in terms of medical images. It doesn't need custom engineering. It will be, and it is, the ones that are available right now are GUI driven by hospital staff. Companies don't like that. So big companies, big PAC companies don't like that the hospital staff can do it. So you have easy to use GUIs, and they can transfer data. They can give rights for reading and writing of files themselves. They don't like it. And scales to meet data growth, I like to hear that. As somebody who is involved with big data is getting prepared to process big medical data. So VNA is incoming. Many people are pushing. So if you look at the present time, we have something like this. So you are inside one hospital, but radiology PACS cannot talk to cardiology PACS because this is from Philips, this is from GE, this is from whatever, Fujifilm. So it's a mess. So and a VNA system would make it then everybody comes to under a unified vendor-neutral archive. And if we have it here, then hospitals can make the decision themselves to open it up, let's say for a big research project. Then we can truly access big medical data. So how big is medical data? Nobody knows. Nobody seems to know. Well, number of images, medical images, double every 5 years almost. More than 80% of that is unstructured. I couldn't understand it at the beginning. So 5-6 years ago, I had discussions with a colleague from UHN. And I was like, what do you mean unstructured? So we have DICOM, we have bags, so we have these headers in the file. That must be structured. No, it is not. So give you a very simple example. Most of the time, annotations, if it is CT and MR, they are written as 1 or 2 lines in the header of DICOM. If you're using ultrasound machines, doctors burn the annotation into the image. They are not supposed to do that, but they do it because it's easier for them. Now guess what part of the medical imaging is ultrasound? Huge part, because ultrasound machines are cheap, they are mobile, everybody's using them from small practice to small and medium-sized clinics. So there is no tagging. So in spite of DICOM, we don't have anything for tagging in place. So what we need for large-scale content-based image retrieval, and I will show you one example of what that means. We need tags. I need a tag for that. I need visual tags. I need visual clues. We don't have something like that. So a big part of that is algorithmic. We have not done work enough on the algorithmic side to be able to tag images properly. But part of it is also formats. So veracity is particularly significant. So artifacts in MR, speckle noise in ultrasound, and many other things. What happens if a slice is missing, and many other questions that are relevant in medical imaging. So beside of the first V's, the fourth V for medical imaging is very, very important. So we have, the estimate is 2 trillion images per year. 2 trillion medical images across the planet. I came up with this estimate because we have roughly 800 billion images in US alone. US is roughly 50% of the world market in pretty much everything. So you can extrapolate and calculate how many images we capture worldwide. So that's approximately 450 petabyte for 1 year, medical images. And keep in mind, every 5 years it doubles. Now, if we are looking for the past 10 years, and you have to look, you want to extract something, you cannot just go with the images of this year. Actually, as required by regulatory bodies, we have to keep medical images of every patient for many years. That goes, depending on the country, from 5 to 25 years, we have to keep them. That's a huge storage problem for hospitals. And this is a big expenditure for them. They have to save it up to 25 years, just in case the patient comes back and need to know what was 12 years ago that we captured some x-rays from the patient. So if you are going to just look at the last 10 years, so we are talking about 4.5 exabyte of data worldwide. Okay, that's really too big and nobody can process it. Give me something tangible. Okay, breast ultrasound in North America. So I only want to work on breast ultrasound, and this is North America. Everything can easily get connected. This is possible. We should be able to do that. That's 100 plus petabyte. So if I upload, as a radiologist, a ultrasound scan of a suspicious mass, I'm not sure. I'm sitting in my small office in some remote village in southern US, and I upload this and say, okay, is there a case similar to this? And I take it, compare it with 100 petabyte of image data, come back with 20 similar cases and say, look, I found similar cases. What is similar? Not the image. The suspicious mass is ROI based, is selective. There is no tagging and there is no intelligent technique to detect those areas right now. In spite of all those billions of papers that we published on segmentation, and all of them are useless, we don't have any tagging for medical images. I want to tag a specific part. It has to be manual. Manual for petabyte data, who should do that? Nobody will be able to do that. So if you're finding breast malignancy for better diagnosis, according to BI-RADS, so 100 petabyte North America alone. So it's huge. Put it in context. Wikipedia is 10 gigabyte. Web is 1 petabyte. The Large Hadron Collider is 15 petabyte data per year. So we are talking 100 plus. doubles every 5 years. So yes, the human genomics, the Human Genome Project, that's huge, 7,000 petabytes. So that's really, nobody can contest. This is big data. And you cannot do personalized medicine without this and without this. And when you say personalized medicine, when I go to the doctor, I'm sitting there, within 5 minutes, everything has to come. Okay, tomorrow everything has to come. And the doctor will send me an email. But we don't have 10 weeks time for personalized medicine. So what happens if some part of my gene is going to be compared with this, or the scan of my prostate is going to be compared with 120 petabyte of ultrasound of prostate. So how are we going to do this? Everybody talks about personalized medicine. What is personalized medicine? If you cannot exploit big data. So big data supported diagnosis is fundamentally for medical imaging content-based image retrieval. It's there, we are working on that since more than 15 years. I don't know how many papers we have published in that area. 2,000, 3,000, 5,000 papers. So now this is the task. I look at a mammogram and I see a suspicious mass. And nobody knows what that is. You cannot really say what that is. It looks regular, so it could be a cyst. Who knows? The breast density may not allow me to really make a good radiological diagnosis because nobody makes an actual diagnosis based on image data. So I get suspicious, and then I have to send the patient to biopsy. And only after biopsy we say, yes, it is cancer. So if I send this as a query to our digital universe, actually I was reading that our digital universe right now is 2.7 zettabyte. I don't know who has measured that or how we have estimated that, but I would say, yeah, okay, 3 zettabyte. So for medical images for a specific anatomy and a specific modality, it will be in petabyte region. So I'm talking only about X-rays and I'm talking about breast. We can have structures for that. We can separate the distributed computing. That's not a big deal. So I'm talking petabytes. So if I go and compare it with petabyte data, I have to come back within minutes and say I found n similar images with biopsy and treatment results. So I show you 10 cases that are strikingly similar to your cases. And say, okay, I found this. The result of biopsy was this, positive, 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 positive. And the treatment was radiation plus surgery, radiation plus chemo, and so on, and so on. And this is the success rate for. So the doctor can make a very informed decision. Again, look, even with big data, nobody will replace the human operator. We just want to provide more information. Nobody can. No, there is no artificial intelligence that can. The guys who said that, they are out of the window. That's the reason that we don't even use the word artificial intelligence anymore. We say machine learning. Because people have bad experience with us, especially investors. So labels, artificial intelligence, machine learning, machine intelligence, computational intelligence, soft computing, so all of them are the same. So you may talk to some colleagues, they are very sensitive to using the word, who cares? Talk to the users, they don't care. They say, give me a smart algorithm that can do the job. Call it whatever you want. But well, right now, again, we don't talk much about machine intelligence. We talk about machine learning. I prefer intelligence mainly because the machine learning community ignores 2-3 classes of techniques. For example, evolutionary techniques are not included in that because they are regarded optimization. Or evolving rule generation is not involved in that. I don't know for whatever reason. So I add those 2-3 and then call it machine intelligence. But down the road, everything is the same. So everybody cooks with water. So what is intelligence? So since 1994, as 52 intelligent researchers signed this, they signed it. So they cannot deny it. So we said that. So a very general mental capability that, among other things, involves the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience. But also they continue that it rather reflects a broader and deeper capability for comprehending our surroundings, catching on, making sense of things, or figuring out what to do. When was the last time that you heard a scientist talk like that? So figuring out what to do. So that's fundamentally the task for big data. So I give you the data, you figure out what to do. You figure out what's the sense of the data. If that's the meaning of intelligence, big data processing, big data analytics has to be intelligent. There is no other way to do it. So what is intelligent? We know the Turing test. Yeah, somebody is here. I have a human being here. I have a computer here. I ask questions. Two answers come. And the question is, how long will it take the judge to realize who is the human and who is the computer? How long would that take? Alan Turing came up with this test to say, if the computer is really intelligent, it should take many hours for the judge to figure out in which of the rooms is the computer sitting. Of course, this has been challenged, among others, by the so-called Chinese room, that, yeah, somebody is sitting inside a room. He doesn't speak Chinese. By the way, there is no language that is Chinese. So, but OK, so it's in the philosophical books. So somebody is here. He doesn't speak Chinese, but he has a book of rules. He has a dictionary of Chinese language. And you give him Chinese text. And by following the rules and reading the manual and using the dictionary, he can translate every Chinese text that you give him. And the question is does this guy speak Chinese? Of course not. So, and the point was, OK, so if you really hard code everything, can you talk of intelligence? It seems not. So intelligence has to be something else. So the main tasks for machine intelligence are classification, recognition, prediction, optimization, approximation, and many other things. So you can take any of this and reformulate every other task that everybody gives you as that. I can understand everything as approximation. Anything you give me is an input-output relationship, and it's so complicated that nobody can give you that function that describes the relationship between in and output, so I approximate that relationship somehow. So it doesn't really matter, but at some point, we have to do some of this task explicitly. So focusing on learning, learning is improving at a task, a set of skills with experience. So that's what generally we understand as learning. In human relationship, we can discuss that. We can debate that. But for computer, I guess experience is data. Experience is data. The more data you have, the better you get for most intelligent techniques. However, more data requires more computational power and storage. So theoretically, a neural network can approximate anything, any level of nonlinearity. So since SVM, we know that we don't use neural networks for classification anymore. It just doesn't make sense anymore. But for approximation, for prediction, why not? But still, we have to struggle to get enough data to do it. But even if you get your hands on enough data, you don't have the computational devices to carry on unless you have a supercomputer. OK, coming to my being a medical imaging guy, working on some aspect of machine intelligence, past 2-3 years, my favorite topic within big data has been Hadoop. Hadoop is by far, this is really something that can fascinate an academic. So back then, I mean the time that we had the first web browser Mosaic, and then after that Netscape and so on. And Alta Vista was the search engine. So back then, we were using supercomputers. So high-performance computing was in. So everybody was talking about high-performance computing. And high-performance computing was fundamentally for the guys who had the money, who could go and get and buy a supercomputer. That was fundamentally the reason Alta Vista was there. So you cannot compete with one computer with this. But then two crazy guys came up with the idea, OK, what happens if I put several computers together, connect them? Can I beat the supercomputer? You know, no academic comes to this idea, because I remember I had in third year of my combined engineering computer science education, the parallel algorithm course. And I hated that course because I didn't know what the prof was talking about. For one term, we talked and talked and talked. At the end, I had no idea how do we parallelize algorithms. So it seems at the end, the resume was, it is a specific task. You have to redo it for every other application again. Well, so why didn't you say that at the beginning of the course? I would not have taken the course. So around the same time that we were fascinated by HPC, and we were analyzing that we can actually not come up with a generic approach to parallelizing algorithm, well, the Google guys did that. They came up with the first one and said, yeah, OK, we don't have money to buy a supercomputer. We just connect 10, 20 computers and see what we can do with it. But that's a hell of a work on the software side. So somewhere the performance has to come from somewhere. Either you have powerful hardware, and then you need a simple software system, well, comparatively, or you have a simple hardware system, and you have to compensate with sophisticated software. Because how do you distribute the data? How do you read it? How do you shuffle the data? So fundamentally, the idea that was here was, don't bring the data to me to process. Let me come to the data. Genius. So these simple ideas that only the practice can force you to do it. I apologize to all colleagues. This type of idea never come to you at the university. And I'm a university guy. So because you have to think practically, you have to think pragmatically. You need a solution in 2 weeks. There is no time for doing 3 PhDs on it. So you have to do it. So it has to be simple. So nobody knew. Of course, everybody was envious, and everybody was puzzling, how did Google do it? And by 2003 and 2004, Google published 2 papers. Up to then, nobody really knew what's going on. Even you could guess what they have done. But then 2003, Google published a paper on GFS, the Google file system, and 2004, a paper on MapReduce. So MapReduce is, again, the practical implementation of the thing that every one of us knows, divide and conquer. But we didn't want to do that because we were so in love with HPC, with high performance computing. We didn't want to go back and sit down and say, how can I apply this idea of divide and conquer that we talk about it every day when we teach recursive algorithms to our students? How can I apply that on parallel computing? So can it be that parallelization of algorithm has something to do with divide and conquer? We didn't spend the time on it. 2 guys, well, indirectly that comes also from university. Everybody who's working at a company has studied at some university. And they go and materialize on the knowledge that they have learned. But it's interesting to see how big a difference it is than academic versus industrial environment. So before that, 2 guys called Doug Katting and Mike Caffarella were working on a different type of search engine, Nudge. And 2003, 2004, when GFS and MapReduce was published, not with all details, by the way, read those papers. There are not much details in that. It's the rough idea, how do we do it? So this guy said, OK, let's do it. Let's take it. And they add DFS, and they call it HDFS. And they add an imitation of MapReduce, basically. And they come up with something that is called Hadoop. So Hadoop is a software package, fundamentally has 2 parts. One is the HDFS, the Hadoop distributing file system, which is an imitation of GFS, which is the Google file system, and the MapReduce, which is an imitation of Google MapReduce. I don't think anybody still knows details about GFS and MapReduce as implemented by Google. Google has not provided any more details. Whatever was done afterwards was done with Yahoo. And then Yahoo at some point published it and made it an Apache project. So made it the public domain. Fantastic. So since then, everybody is a huge community of complete package of software. And so there is a company that was, I mentioned this, I took this from the Cloudera website, and Doug Katting is working at that company. And many, you name it. So is Yahoo, is LinkedIn, is Facebook, is Twitter. Now everybody is using Hadoop. So what is Hadoop? Hadoop is the planet versus Google, basically. So because Google had such a success, and they gave some hints, Guy, we have done it this way with those 2 papers in 2003 and 2004. So Yahoo and some others apparently put a lot of effort into that and basically re-implemented that system based on the clues that they had. And of course, again, if you put your heart and your mind into it, everybody cooks with water. You just need to sit down and say, okay, let's do it. You can do it. Especially if you have such fantastic information processing and computing guys such as Doug Cutting and Mike Caffarella. So there are many technologies involved with this, with Hadoop. Hadoop itself, NoSQL databases, analytic RDBMS, and many things. And meanwhile, there is a huge number of companies involved with that type of products. You can simply go and download Hadoop. So it's open source. So the latest one is 2.6. You can go and download it. It's a server. It's a software. It's a package of software. It's an ecosystem of different packages. And many, many thousands of people are contributing to that. So, but what is it? OK, so it started with HDFS and MapReduce, which is, again, this is an imitation of GFS, and this is an imitation of Google MapReduce. Nobody knows whether it is exactly the same. It doesn't need to be. It seems it's doing the same job. Yahoo is putting this on 42,000 computers. So it must be capable. Otherwise, it cannot run on 42,000 computers. So then you have an HBase. So you have a database, your NoSQL database. You cannot do MySQL here. MySQL is a structured database. It's classical RDBMS. It's relational database. There is no relational database here. And then you have Scoop and others for data integration. So data integration is a big, big deal here. Then you have many, many other things. You have Pig Latin for scripting, Hive for query, Mahout for machine learning. I will give you some examples here. So Pig Latin for scripting. For example, the MapReduce part is really tricky. So if you build a rack yourself, just buy 5 computers. You can build a rack and put the Hadoop on top of it. If you're a good programmer, a week. You can get it up and running in a week. And if you add additional racks and scale up to 5,000 computers, that can happen with no effort because Hadoop scales up by itself. That's the beauty of it. So you can add at any time. So I don't know whether we realize what huge opportunity that is. That's an enormous amount of human knowledge into the Hadoop project. Everything before Google, everything started back in the 50s. That as AI community, we promise, I wasn't even born, but I count myself to that community. As AI community, we promised we have the general problem solver. Oh my God, outrageous. This is preposterous. We promised that we come up with a software that solves any problem. OK, so take it easy. Just let's work on distributed computing. And so Mahout and others provide some machine learning techniques. So then you have Uzi for workflow and scheduling, and you have Zookeeper for coordination. So basically, this is and I have forgotten some of them. I have forgotten, for example, Flume, which is responsible for data streaming, because it's not relevant to what I do. I don't have a stream. I do not expect any streaming in medical imaging. I know where the images are, and the amount of data that is being added is really slow, so it's not a big problem for me. But there are others here. So this is a fluid, living ecosystem of software, and it will grow. It's growing. So and there are other similar systems that I didn't want to mention here because we don't have time. So if you look at number of nodes that everybody is using, I just grabbed some examples. AOL 150, eBay 530, Facebook 1,400, Fox 140, LinkedIn 4,000, Yahoo 42,000. So there are systems in place. They are doing the job. So what is MapReduce? So MapReduce, if I throw a little bit of pseudo Python at you, so if I get a document, and then that document, I count for every word in that document. I split it in words, basically. And then for every word, I assign 1. When I first time saw this, I said, what the hell? What is this? And then you have to always wait what happens afterwards. So you map it, so which is divide. But then you have to reduce it, which is conquering it. So I have to, if I get these guys in a conference or something, I have to ask them, why did you name it like this? There is no intuition behind it. Mapping for me is one-to-one. Well, it is one-to-one in some sense. So, and then reduce, that you get some keys and values. And when you say keys, that's the fundamental difference between distributed computing and relational databases. This is key-based. Everything, because there is no structure. There is no structure. I cannot do row-wise and put it in predefined columns. I have to work with keys. That requires a little bit of rethinking. Well, but again, this is what we have learned. We have learned hashing, for God's sake, when we in our undergrad. Working with keys should not be very difficult. And we know this is big O1. This is the fastest we got in getting access to the data. So, and then I output the keys and sum the values. Well, of course, this example is focusing on the one task that we do every day in web, or Google does, and any other search engine does, which is split a document in many words, count the frequency of the words, come up with a table based on those frequencies and relative probabilities. I search for whatever, Alzheimer, and you show me the websites containing the words Alzheimer. So if the data comes in, I have to map them first, and then I have to reduce them, and I have to reconstruct the data. Of course, in the middle of that, there is a lot of sorting and shuffling going around. That part, the MapReduce, is a huge number of routines, functions, tasks that take care of that. Among others here, so go back, so when you're designing this, see what you have to do. This is distributed computing. What happens if one of the nodes fails? So you have broken down the data. So if one of the nodes fails, the data is lost. What? So you need duplicate. So every piece of information has to be at least on 2 computers. One of them fails, no problem. I copy it on another one. At any time, I have 2 copies of everything. So when you go back and you are designing a MapReduce system, a distributing computing system, you have to think about this sort of stuff, because you don't have the luxury of using a supercomputer. Everything is central. So example, yeah, so I go look at it. So I have some words, some documents. So how many cookies could a good cook cook if a good cook could cook cookies? What is that? So this is a document broken in parts just randomly. A document comes in, you break it down, and then you just separate the words, map it, and each one of them is counted 1 time, right? Because it is 1 time. And then you map it here, and then the reduce part, add everything up, and then you say, okay, the word good is there twice, the word many is there 1, the word cook is there 4 times. So that's what the search engines do. So would this approach help me if I'm doing work on medical images? Of course not. I have to replace the map and reduce function for my case. That's the reason we need the Pig Latin, the scripting language. So it gives you a nice interface to not, if you don't want to make your hands dirty with Java, then the Pig Latin is a very simple scripting language interface that you can develop your own map and reduce. But you have to do something like that for your data. So this is the easiest data, if you like. Well, now is easy after 20 years of internet. Back then it wasn't. So, but everything we know from Occam's razor up to divide and conquer is here. Go implement it, you see, it is here. You cannot do it without those principles. So no new principle has been invented. We have just rethought what we had. It's fantastic. That's the spirit of research, actually. So the Mahout is the part in the ecosystem of Hadoop that is responsible for machine learning. There are many things. For example, matrix factorization is a big thing that you have to do on big data. For example, classification using hidden Markov models, multi-layer perceptron, random forest using many decision trees and things like that. It is in Mahout. And clustering is the really old ones, k-means, up to fuzzy k-means, and many other streaming k-means and so on. The spectral clustering are in there. And dimensionality reduction, of course, how can you do big data and not think about dimensionality reduction? Single value decomposition up to PCA, principal component analysis, and so on and so on. So many, many things are there. And this is actually, Hadoop is one of the parts of Hadoop that is growing really fast. There is an initiative from UC Berkeley. They are working on a similar system with Shark and Spark. I didn't want to mention that here because that would be, we had enough material to cover anyway. So, but many people are working on that, and this is now the contribution of the universities. We can contribute to the machine learning part. We can contribute to algorithmic parts. So we can contribute a lot. But the platform is there. The platform is there to play with and to work with it and to see where we go. So to sum up, so big data analytics, as I introduced this acronym at the NBDA, offers many opportunities. Hadoop and similar ecosystems are crucial for BDA. And big data analytics without machine intelligence cannot be done. You cannot do it. You cannot simply do it. How can I do it? How can I classify data without support vector machines reliably, with some theoretical evidence that it is the best, it is the optimal decision making? Medical imaging can immensely benefit from big data analytics, but we are not ready yet. We are not, well, when I say we are not ready. So hospitals are not ready yet. That's good news for us, because historically we are not very fast either in research. So we would need 5-6 years to come up with some cool ideas, how to use Hadoop-like systems, and we may start with Hadoop and we end up with some other ecosystem, doesn't matter. But whatever comes will be on top of Hadoop. So we will use that experience to make it better, bigger, faster, more efficient. So, and so far, we can only use benchmark data in Hadoop to get ready. So installing, just building a rack of 10 computers, installing 200,000 lung cancer images from Cancer Imaging Archive, there you go. That would take a month. That would take a month. Now start doing some, can you, if I give you the lung CT, can you match it in quasi-real time, come back and say it is similar to this image? Assume there are annotations there. You don't need to do that part. So if you find that, so if the date that we have done it is already 2020 or something, I don't know. By then, I guarantee you, VNA is there, and we have access to the medical data in hospitals. So this talk was supposed to be scratching the surface and hopefully getting some of you motivated, and some of you, I'm sure you are expert in your field and is apparently has some overlap with this. And maybe, who knows, maybe we can initiate some collaborations within the campus. Thanks for listening.